Salutations, Internet. Good time zone. I see you survived the Newton's method video. Good. You could do it. Wasn't too bad, was it? All right. One of the benefits of having a YouTube video series as opposed to a formal class is that I am not bound by time constraints. Right? I don't have to have X number of hours in a week, Y number of weeks in a semester, and I don't need to test you over the material like a traditional class would. This has its pros and cons to it, but one of the pros is that I get to focus on the stuff that I think is important, while I get to skip some of the stuff that I don't think is important. Like a lot of the derivation steps, I don't think that's super important. I think we can skip over a lot of that. I'll be doing that later today. But seeing where the equations come from, I do think is important. And rather than just handing you an equation and saying, this is the equation that you're going to be using, I will actually be showing you, okay, what is the background to it? Why is it important? All things like that. I bring this up because while going through my notes, the next two equations, technically two equations, this topic was just kind of handed to me, and I think I can do a little bit better than that, which is why I'm here. So, that out of the way, let's go ahead and get into today's video, which is time of flights for parabolic trajectories. So going back over here, we've done time of flight equations for closed loop. Now it's time to move on to the open things like parabolas and hyperbolas. I keep wanting to pronounce it parabolas, which is actually something I was going to say. It sounds really I'm tangent, getting lost in a tangent. Anyway, we've done a bunch of closed loop things. Now we're going to play with the open loop things, and we're going to start off by easing in with parabolas, the very specific case scenario. So for this, let's take a look at the angular momentum equation, which for specific angular momentum, that is just going to be h is equal to r squared times theta dot. And yep, sure enough, it's an angular momentum equation. But for our purposes, we're going to go ahead and break it down a little bit. Well, not break it down, but we're going to write it differently. Instead of theta dot, we're going to do d theta dt. And that's going to be important because we're going to need a time element. And look at that, we have explicitly written a time element here. So now we have our angular momentum, and we have a whole host of equations here that we can play around with and sort of plug things in. The thing that we're going to want to plug in next, play around with next, is going to be our orbit equation. And I will be using the h squared over mu variant for this one. So let me write that off to the side so I don't have to keep flipping pages. R is equal to h squared by mu over 1 plus e times the cosine of theta. So now, when we plug our orbit equation into our angular momentum equation, we're going to get h is equal to h to the fourth, right? Because everything in here is just going to get squared. Over mu squared, all over the quantity of 1 plus the eccentricity times the cosine of theta squared times d theta dt. we can clean up this equation a little bit. So we definitely know that we want to have an expression for dt, and it is not going to include anything with theta in it, because that's going to be over on the side of theta anyway. So let's just combine like terms. We'll move the dt over. That's going to look like mu squared over h cubed, differential of time, is equal to, I'm going to write this as a denominator, 1 plus e. And actually, instead of including that, remember, this is the parabolic equation. E is 1, so we can just get rid of that. The 1 is assumed. So we have 1 plus e cosine of theta, quantity squared, under 1. It's the differential of theta. So the differential of time is not something that we care about overly much for this equation set. What we actually want is actually time. For that, we're going to integrate. And so let me scroll down a little bit. This is rough on my wrist. So we have our integrals here. What are the bounds that we want to include for our integrals? Well, and a really easy one is just to look at periapse. Right? So at the time of periapse, we know that our cosine expression is going to be 0. Cool. Then we can take a look at anything from that periapse to any other angle. So we'll just call that theta, and it's going to be the time to that theta. And there we go. We have to find the bounds of that equation. So we have our integral expressions. Now we solve. So we have our constant mu squared over h cubed. And then we have our time, t minus tp, times, and this is one of those parts of understanding that I don't feel the need to dwell on a whole lot. This is going to integrate into 1/2 of tangent times, or 1/2 tangent theta by 2 plus 1/6 tangent cubed theta by 2. And the author of the textbook that I have been referring to for the notes for this episode defines this as a relatively simple equation, which, I mean, it kind of is. It's simpler than this, but I would not look at this and go, oh, that's simple. So I have one question for the author. Are you doing all right? You doing all right, dude? Anyway, now that that joke has been made, this is passable. This is certainly the equation, but it is messy. So we're going to take a look at this term and this term. This cubed here is just for the whole, the tangent value as a whole. For those of you who don't get to deal with tangent cubed all that much. And we see that they are a shared term, a shared expression, so we can give ourselves a variable and define it as that expression. So we will have B be defined as the tangent of theta over 2. And I'm going to box this in because while it may not be an equation that gives us a final answer that we really care about, it does help us with this. And that is definitely something that I don't want to lose track of. This, by the way, is called the parabolic anomaly. Parabolic anomaly. Cool. So I don't need to scroll down. I keep doing that. Last thing that we're going to do before we write the final version of this equation, I'm going to make another side note here. And we have a term of mu and h. And so going back over to here, we can perhaps make that a little bit neater by converting that by taking that h and converting it to p. It might be more useful, might not be more useful. At least for when I was prepping for this episode, I thought it was a lot more useful, so that's what we're going to go with. So the angular momentum is equal to the square root of the parameter p times the gravitational parameter mu, which when plugged in over at that term, we have mu squared, which I am actually going to write it as 4 halves over h cubed. So that becomes the square root of p cubed mu cubed, which with our exponent math, we will turn that into, not beta, we will turn that into p to the 3 halves and mu to the 3 halves. And once all of your matrix math has been taken care of, matrix math, I legitimately don't know where that came from. When you have taken care of all of your exponent math, you will have the square root of mu over p cubed. And so when you solve for your t difference, p minus t sub p is equal to the square root of p cubed. If I can make that look a little bit better. P cubed, much better, by mu times 1/2 b plus 1/6 b cubed. And that is actually the final expression. That is actually the final expression that we care about. So now we have our time of flight equations for parabolas. Wasn't too bad. But now, let's test it so that we can get a better understanding of just what's going on with it. All right, so give me just one moment. I will be right back. All right. So, in a previous episode, we talked about Sputnik leaving the Earth to go sightseeing around the solar system, right? So one of those stops that Sputnik is making is around Mars. And here we have the mass of Mars and the parameter for the trajectory that we are going to be using. We said going around, orbiting around, but we're not orbiting. We are just passing by Mars. This value down here, the astute among you may remember from the last time we dealt with parabolas, that's theta infinity, the air quotes outbound angle, is actually going to be 180 degrees. So this is 167 and change. What's going on here? Well, if we go all the way back to the first video that I posted, I talked about perturbations from outside forces to the two-body problem, that the two-body problem is a simplification. And perhaps this is the best time to talk about it. The two-body problem exists inside of the sphere of influence of your host body. Outside of that, in this example, the sun starts weighing in way too much for us to use a simple two-body expression, or two-body set of equations. So, through some estimations with mathematics, I have given this value as the approximate angle that we will be entering the sphere of influence on our orbit. This is still a parabolic trajectory. Don't get me wrong, this is not hyperbolic, but this is just taking in a little bit of extra realism to take into account that, yeah, Mars does not exist without anything else around it. Mars orbits the sun. So there's my reasoning for including that there. And with this set of givens, we want to find two things. I want to find the amount of time that we spend inside of the sphere of influence of the Martian sphere, I guess. And just to confuse you with an extra bit of lore, let's say that Sputnik has a number of sensors on board that will help us with readings for approaches to Mars. So we want from the sphere of influence all the way down to 10,000 kilometers. And 10,000 is just an arbitrary number that I selected in this case. But maybe I selected it because the instruments on board will not give us any more useful data past the 10,000 radius mark. Who knows? So now we have our desirables here. Cool. Let's get started. I'm actually not going to scroll down this time. I'm going to scroll up. So we know that for this equation here, one of the things that we absolutely need is the parabolic anomaly term. We need to know what that is. So let's solve for that first. Scrolling back down here. Our B is equal to the tangent of, and we're going to go from the sphere of influence for this one. So 167.36 degrees divided by 2 to give us a parabolic anomaly value of 9.028989.769 degrees. No, not degrees. We already used degrees here. Okay. Then radians. Also no. See, this is just a dimensionless value. I'm not going to write it out because I'm just going to get rid of it. Our B value is just a dimensionless value. We only care about the quantity of it. We don't have any units associated with it. So there you have it. There's that. All right, we're going to scroll down a little bit more. And we have T minus TP is equal to the square root of our P value, which is 14,000 kilometers cubed over mu. And, excuse me. And this is a good opportunity to practice something that I've kind of neglected for the last few episodes. We were given a mass, we want the gravitational parameter. So, the mu of Mars is going to be 6.4169 times 10 to the 23rd. Yeah, I copied that down, right? Good. Times, over here on our equation sheet, I included the gravitational constant. That's the word for it. I almost called it a parameter again. So 6.66743, 6.66743 times 10 to the minus 11. And it's going to give us a value of 4.278, and I'll stop there, times 10 to the 13th kilograms meters cubed. We don't want meters cubed, we want kilometers cubed, because everything we're doing is in terms of kilometers. So we will divide this by 1,000 cubed, give us 4.278 times 10 to the 4th kilograms per kilometer cubed. We'll go ahead, put the label back on it. Maybe I'll put the label back on it. There we go. All right, so there is our mu value. We'll plug that in. 4.278 times 10 to the 4th. Extend those out. Make sure that's closed. Times, actually, it's bigger. Times, ooh, fancy. 9.028989769 over 2 plus that same value, 9.028989769 cubed over 6 to give us a value of 1,018,668.1 seconds. But hold on just one moment. That's not our final value. That is the value for the entire inbound leg, from when we entered our sphere of influence to periapse. So we need twice that to get the entire sphere of influence time. And that's just going to be 2,037,336.2 seconds. And that is the value that we want. So now we need to find, for our purposes, we need to find what angle we reach 10,000 kilometers at. So coming down to, yeah, I'll give us a full page. So easiest way to do that, just use your orbit equation. So R is equal to P over 1 plus, again, E is going to be 1, so cosine of theta. And then you solve for theta. I'm going to skip a bunch of steps because I don't need to do the derivation every single time. It's E minus R over R. Double checking. Yes. And so plugging in the values of the arc cosine of, we know P is going to be 14,000. The radius that we care about is 10,000. That's going to give us an angle of 66.42182152 degrees. All right. So now we have another theta. We can plug that into our B equation, and then we can plug that into our time of flight equation. Nice and simple. Four, 2, 1, 8, 2, 1, 5, 2 degrees over 2. To give us a value of 0.654653671. Scrolling down a bit more. Now we have E minus TP is equal to square root of 14,000 cubed over 4.278 times 10 to the 4th times 0.654653671 over 2 plus 0.654653671 cubed over 6. That will give us a value of 2,996.0 seconds. Now again, this is the time from periaps to our 10,000 kilometer radius. What we want then is to subtract the time from when we entered the sphere of influence, which is going to be this one up here, not this one, not our final answer for that section. It's going to be that answer minus the 2,996 number. So be 1018 double checking 668.1 668.1 minus 2,996.0, and that will give us a final value. I'm going to go ahead and just write this whole thing in here. Going to give us 1,015,672.1 seconds. Or for those of us who don't think in exclusively seconds, it's going to be 11 days, 18 hours, 7 minutes, and 52.1 seconds. So that's how long we would need to have that set of sensors activated and recording, which is a fairly long time. That's almost 2 weeks. So in a different series, we'll discuss if that's realistic or not. But for now, we have our time of flight equations, or our time of flight values for our problem statement. And with that in mind, I think this is a pretty good place to end the video. So thank you all so much for stopping by.